Okay, hi again everyone. We are now on page, let me see, I forgot, 26. And this is video example 26C of our statistics class, I'm sorry, of our Calculus 3 class notes. And we just got done on the last page understanding how to take the derivative of a vector value function. And in these figures, I was just trying to show you graphically what is going on. So if I'm traveling along this particle path, represent, so here's the particle at the point P at time t, and some little time later the particle has traveled along the path to this point Q. So this is the vector r of t, this is the vector r of t plus delta t. So r of t plus delta t, subtracting r of t, so if you subtract r of t, it would come down this way, and then the resultant vector would be here, but we can easily just put it up here to show how it works better graphically between these two vectors. So this is the vector right here, r of t plus delta t minus r of t. Now what is that derivative vector r prime of t? So r prime of t is tangent to the particle's path, the curve right here that the particle is traveling along, tangent to the particle's path at the point P, which is where the particle is at time t. So it's tangent there, r prime of t. And this r of t plus t minus r of t divided by delta t, I could easily have drawn that over here. It's this guy shortened or lengthened depending on what happens when you divide by delta t. I just didn't want to clutter it up over here, but it could be over here as well. But putting it over here at Q, because r of t plus delta t is where I'm at there, this is what it looks like. It's not tangent because I have to take the limit as delta t approaches 0, which means this Q would be walking back along the curve, getting closer and closer because delta t is approaching 0. Then it's the tangent vector, which is what we want. So the tangent line to the curve at a point f of t naught, g of t naught, h of t naught, so that's the x coordinate, the y coordinate, and the z coordinate, when we have our parameterized curve, which is represented by the vector value function r of t, is defined to be the line through the point parallel to r prime of t naught. Of course, the curve must be differentiable, smooth. All of these guys must be able to take a derivative of, which means we require that the curve is continuous with no sharp corners or cusps. So what are the parametric equations for any line? Any line through the point x naught, y naught, z naught, and parallel to the vector v, which has components v1, v2, v3, we recall that these are what they are, right? So what are the parametric equations for the tangent line to r of t at t equals t naught? In other words, through the point f of t naught, g of t naught, h of t naught, which is like x naught, y naught, z naught, and parallel to r prime of t naught. So this is my vector v if I'm looking at the general parametric equations for a line. So then you can simply write down that x is f of t naught plus t f prime of t naught, and y is like this, etc. Okay, so easy to find the parametric equations for the tangent line if you can find r prime of t. So definitions: if r is the position vector of a particle moving along a smooth curve in space, then the velocity of that particle is dr dt, or r prime of t, and that's tangent to the curve. At any time t, the direction of v is the direction of motion. So if somebody says in what direction is a particle moving, they're asking for what's the direction of v. It just means give me v divided by its magnitude to give me a unit vector, but that indicates the direction. Magnitude of v is the particle speed. The derivative a, which is dv dt, that's the acceleration. When it exists, is the particle's acceleration. So in summary, here's what we have. Velocity is the derivative of position. Speed is the magnitude of velocity. Acceleration is the derivative of velocity. So this is all familiar from Calc 1, hopefully. And then the unit vector v divided by its own length is the direction of motion at time t.